Okay, let's start the third chapter of this class, which is about aggregation and segregation. And finally, we're going to learn how to build the first type of building blocks. Remember the definition of building blocks? They are simple simulation models that can be used to create more complex models. And in this course, we will discuss several types of building blocks. The first type is aggregation and segregation. I will introduce how to use simulation models to simulate the process of aggregation and segregation. Okay, and in future, if you are interested in a specific application or research that needs the simulation of aggregation and segregation, you might want to get back to find some models in this chapter to implement the process, the pattern you want to produce. Okay, let's get started. Yeah. First thing first, before going into the word of aggregation and segregation, I want to mention this professor, Tobler. It should be W.R. Tobler, so Professor Tobler. He used to be a professor in the University of Michigan, okay? And he is very famous for this first law of geography, okay? As a student in GS major or in geography, you should know this. If you didn't know it, it's okay. And now this is the first law of geography. Everything is related to everything else, but near things are more related than distant or remote things. Okay, this looks like a very simple and straightforward sentence, and you may think that, okay, this is kind of obvious because I'm a student in GS major. I know that there is something called spatial relationship, and there is spatial pattern, and the spatial pattern is based on the spatial relationship, right? But you should know that this idea of spatial autocorrelation, the idea of spatial analysis, they are all based on this first law of geography. And it was proposed by Professor Tobler in 1970. Back then, nobody summarized um, this knowledge within a sentence, okay? And why is this important? But before that, before we can discuss the importance of this first law of geography, this is a fundamental equation of geography, which means that we translate that first law of geography into mathematical language. So here, Gij is the interaction between locations. Dij is the distance between locations. So Gij is positively correlated with the reciprocal of distance, which means that this distance between locations will affect the value of this function. And the value of this function is positively correlated with the interaction between locations. But you should know that the larger the distance, the smaller smaller the independent variable here, right? Which means that the the relationship between Gij and the Dij is negative, which means that the closer the distance, the stronger the interaction between locations. The longer the distance, the larger the Dij, the smaller the Gij, the weaker the interaction between locations, okay? And the first law of geography actually reveals something called spatial dependency, or you can say it claims that there is something happening within any space with geographic entities, and this something is called spatial dependency. It is the tendency for things proximal in space to be related. This relationship could be positive, could be negative, right? There might be a chiral relationship, which means something caused something else. But this causality could be there, could be not there. You're not sure, but there must be some kind of correlation. This correlation is statistical, of course, right? And there might be this relationship might be caused by something underlying, by the same underlying thing, okay? And there is also spatial heterogeneity. Because there is spatial dependency, similar things, they tend to be get together. And that's the reason why we have clusters within a specific space. For example, in Ohio, we have clusters of cities, right? Columbus is a cluster, and Cincinnati is another one. Cleveland is another one, right? And besides all those big cities, most regions in Ohio, they are rural areas, right? So this is spatial heterogeneity, uneven distribution of a trait, event, or relationship across space. For that example I used for Ohio, the uneven distribution of urbanized areas and rural areas, that is spatial heterogeneity, right? Here is an example. Yeah, I'll show you these two examples simultaneously. On the left side, annual average precipitation across the whole country, and you can see that different colors, they are for different levels of precipitation. Obviously, on the right side of this map, precipitation is higher than the left side of the map, which is the west part of this country, right? So heterogeneity, right? Green areas that clustered on the east side of the country, and yellow areas, which means they have pretty low annual average precipitation. They are clustered on the west side of the country. Spatial heterogeneity. And this map is just verifying the claim I just made one slide before, right? There are clusters of cities, right? Columbus, Cleveland, Cincinnati. I think that's Cincinnati, right? Not sure, but you can say this spatial heterogeneity in terms of population, right? We still have other smaller cities, but there are small clusters, and among these clusters, there are rural areas, okay? The word is patchy. You can consider each cluster as a small patch. You can consider those areas with similar levels of precipitation. They form a patch, right? They form a patch. And here, another example, high resolution ethnic group of Detroit in terms of different, of course, ethnic groups, right? Blue is for African American, a red is for Anglo-American, right? White American. Yellow is for Hispanic. Green is for Asian. So yeah, again, a good example for our patchy world, but this time is for a patchy city. It's for a patchy city, right? So spatial dependency and heterogeneity, they are the core of GIS science. And who claimed the existence of them? Who revealed them? The first law of geography. So that's the importance of first law of geography. It is the very foundation of spatial analysis, because spatial analysis is based on spatial dependency and spatial heterogeneity. So if TFL, the first law of geography, was not correct, GIS would not be useful, because the whole GIS, the geographic information science, here S is not for system, is for science, is based on the assumption that all those geographic entities within space, they are somehow correlated, right? If that assumption is incorrect, then there is no GIS, right? And the maps would not be used for, and the life as we know it would not be possible. And techniques that rely on TFL include spatial autocorrelation, spatial interpolation, and GWR, and etc. They are all based on the assumption that all those entities within any space, a real world space or a virtual space in NetLogo, they are all correlated somehow. And we do analysis based on that assumption. Okay, so local interactions among distributed entities matter, spatial context matters, geography matters. So that's the importance of the first law of geography. I think this is important enough, right? If it was not there, we would not talk about GIS today. And here are some papers giving comments and discussing the first law of geography, or Tobler's first law, whatever you want to call it. These are review papers, and they are available at Canvas. If you're interested in them, you can go there and download and read, okay? And here, what's the challenge for us if we want to simulate spatial patterns, spatial processes? If we want to simulate the very basic of the basics of spatial patterns, which are aggregation and segregation. Okay, we want to use simulation models to simulate aggregation and segregation. Okay, and you should know that simulating them could be tricky. Okay, and aggregation means spatial clustering of similar things. Segregation refers to spatial separation of different things. But you should know they are happening simultaneously. If there is aggregation, it means that there is segregation. Aggregation can arise from a segregation mechanism favoring the separation of dissimilar entities. There used to be racial segregation in US, right? Back then, because of laws, Black people and white people, they were separated from each other. And then there were Black communities and white communities, right? So each community with a specific racial context is an aggregation, right? And on the other hand, segregation can arise from an aggregation mechanism favoring the clustering of similar entities. So you cannot separate them. You cannot separate aggregation and segregation. Okay, you should know that. And how to address that? How to address aggregation and segregation using simulation models? First thing, we need to simulate something called space, because no matter aggregation, segregation, they should happen within a specific space, right? So here in computer science, when we're trying to use simulation models to address space, we use a lattice of cells, like a chessboard. And here it is. It is a chessboard, right? And there is a grade on this board, on this chessboard, and we have small cells. So this space is a lattice of cells, and we're using some special method is called Toreto wrapping to make this chessboard an infinite space. Top and bottom are connected, left and right are connected. So toroidal wrapping eliminates boundary effects, which means that if you are living on this board, right, you are an agent here. If you are moving to the very left of the board, and if you are stepping out from the left side, you will immediately appear on the right side of this board. Similarly, if you are going north and you reach the northern boundary of this board and you step one more, you take another step, you take one more step, you will disappear here and appear again from the bottom of this board. So you can never escape from it. Okay, so boundary effects, we're going to talk about it because the spatial pattern is relatively simple to address in the middle of the space. But if this space has boundaries, it's kind of difficult to address the spatial pattern along boundaries. Okay, so here, how to solve that? One problem is that just make this work infinite. If something is going to disappear from one side of the board, let it appear on the other side of the board. Okay, that's it. And how to address time? We use iterative updates of cell states. And we use integer time called clock ticks. Right? Contrast with continuous time. Here we use discrete time, which means that each cell has a specific state at a specific time. Could be 0, could be 1, could be empty, could be occupied, could be black, could be white, could be red, could be yellow, could be anything. But this state can change by time. But how to define time? We use something called tick. It's just like a tick from the clock, right? A tick could represent a second, an hour, a week, a month, or 1 million years. It depends on your simulation, depends on your context, but it doesn't matter. We use something called tick to represent time. And after each tick, the state of a specific cell could change, could stay the same, but for each state, for each tick, there is a specific state for each cell. Okay, so tick 1, for example, this cell here, right? It's empty right now. So this is the state of this cell after the last tick. Let's just assume there was a tick. And suddenly there is another tick. And after that tick in future, I know, let's just assume it will still be empty, but it doesn't matter. It means that the state of the cell does not change after the next tick. But that's a tick. Time has gone. One tick has gone. Okay. So how to address time and space using NetLogo, using simulation models? We simply use this lattice of cells. Okay. And how about neighborhoods? We need to define neighborhoods in order to simulate things. It's pretty important. Later you will know why. You will use this whole semester to know how to address neighborhoods. So the meaning of neighborhoods, the importance of neighborhoods is that you need to know how to define adjacent or connected or disconnected. We use the definition of neighborhood to do that. So here, usually we have two methods to define neighborhood. The first method is called Van Neumann neighborhood, a neighborhood with radius equals 1. In the Rook's case, Rook is from the chess, right? Rook can go forward, backward, left, right, but cannot go diagonal directions, right? This consists of 4 orthogonal cells, the cell above, below, to the left, to the right of the target cell. So here is the example. If the target cell, or we say the central cell, is this red cell, if we define a Van Neumann neighborhood, it means that only these 4 blue cells, they are neighbors of this red cell. All these blue cells, they are on what? Orthogonal directions of this what? Of this red cell. North, south, west, east. Okay? So the next method seems obvious. It's called more neighborhood. A neighborhood with radius equals 1. In the queen's case, in chess, queen can go along all 8 directions, orthogonal or what? Diagonal, right? This is an enlargement of the von Neumann neighborhood to contain diagonal cells. So now if we are using more neighborhood, you can see that all other cells, all 4 other cells, on the diagonal directions of the central cell, they are also included in this neighborhood. So it's pretty important to address the nature of neighborhood in your simulation. Are you using von Neumann neighborhood or are you using more neighborhood? Because that from if we are talking about the radius of a neighborhood, it's always 1. What does it mean? So the distance from, for von Neumann neighborhood, the distance from this red cell to all 4 blue cells is 1. It makes sense, right? But in more neighborhood, the distance from this red cell to all 4 diagonal cells is also 1, although the physical distance is not 1, right? Because all these 4 cells, they are on diagonal directions. Their actual distance, let's just say the centroid of this top left cell, if we measure the centroid of this cell and the distance between the centroid of this cell and the red cell, this distance obviously is not equal to 1 if we define 1 as the distance between the centroid of this red cell and the centroid of this blue cell. If this distance is 1, then distance between these 2 centroids, it's not 1. If we are talking about Euclidean distance, actual distance. But since we have defined the more neighborhood, the distance from central cell to any one neighborhood is 1. Okay, but yeah, that distancing, you can, for now, you can ignore it. Okay, but now you should know, commonly, usually, we use 2 methods to define neighborhoods. Okay, von Neumann or more neighborhood. You would ask, which one should I use when I'm trying to simulate something? Well, there is no correct answer. Again, you will see this, you will hear this a lot in this class. There is no correct answer. It depends on your application. It depends on your interest. Okay, so that's it. 2 types of neighborhood here. Okay, von Neumann neighborhood and more neighborhood. So how to update cell states? Like I said, we update cell states by time, and time is addressed by ticks, right? At a given moment, each cell is in one of a set of discrete and finite of states. It means that you should give a specific number. Sorry, let me put it this way. There should be a limited number of states for each cell. Could be binary, which means 0 or 1, black or white, or a red or blue. That's 2 states, right? There could be 3 states, 0, 1, 2. Could be 4 states, 0, 1, 2, 3. But there should be finite states. Okay, and usually cell state is a function of states in its neighborhood. What does it mean? It means that for each cell, its state is affected by its neighborhood. If we translate this into a mathematical expression, it's called cell state is a function of states in its neighborhood. Function means that they are connected. Cell state is affected, is connected to what? To states in its neighborhood. Here, now you know the importance of the definition of neighborhood, because depending on the different definitions of neighborhood, your results, your cell state could be different, right? You need to be clear with the definition of your neighborhood, okay? And we have two types of updating. Synchronous updating, all cells determine their next state at the same time. Usually, you can say before a tick or during a tick, but it doesn't matter. For that chessboard, all cells, they're going to determine their next state at the same time, simultaneously. And there is another method for updating is called asynchronous updating. One cell at a time is updated. So usually, we choose a random cell on the chessboard or several cells. That's more complex. Let's just say one for now, okay? After one tick, only one cell will change its state. Okay, not all cells like synchronous updating. This is the reason why it's called asynchronous, right? And ticks, single movement of model clock, right? It is used to address time. And generation, let's just define generation. For synchronous updating, one tick is a generation. We usually, that's a convention. For asynchronous updating, a number of ticks equal to number of cells, which means that if there are 89 cells on your chessboard in this space, 89 cells. If you are using asynchronous updating, how many ticks do you need to update 81 cells? Of course, 81 ticks, right? So in that case, after 81 ticks, we call it a generation. Okay, so the generation, the definition of generation changes, and it depends on your method of updating. Okay, okay. And yeah, I will just stop here for this video, and from next video, I'm going to introduce the very basic way to address aggregation and segregation using simulation models. And we're going to talk about something called local averaging. Okay, thank you.